Hello and welcome to this video for CE108 Mechanics of Deformable Solids. We are still in chapter number 3 about the mechanical properties of materials. We're trying to, in this chapter, to understand the relationship between the cause of the deformation, which is the stress, and the consequence, which is the strain. So in the previous chapter, the previous section, we defined what the strain is. We defined why it's important to define the strain rather than the deformation itself. And we define what is the normal strain, which is an elongation or a shrinkage, and the shear strain, which is a change in the shape of the material without changing its volume. So now what we are going to do in this second section of this chapter is to focus more on what is the relationship between the stress and the strain for a given material, and how does it depend on the type of material, on the properties of the material. So one way to describe the relationship between the stress and the strain for a given material is to draw its stress-strain diagram. And the way we obtain this stress-stress diagram is to take a given material that is attached at one of its extremity, and then you start to apply, for example, if you want to look at the stress-stress diagram during an actual load deformation, you will apply a normal stress on this deformation, and as a function of the stress that you apply, you will track what is the corresponding elongation. So you will track the corresponding strain, or you will apply a given deformation. So you will apply a given strain, and you will track the corresponding stress that you have to apply to do this deformation. So either you fix the deformation and you measure the strain, either you fix the deformation, so you fix the strain and you measure the stress, or you fix the stress and you measure the strain. In this case, we are going to focus on the stress-strain curve, the stress-strain diagram, in the case where you fix the deformation. So we are going to say, in this case, it's going to be displacement control. You fix the displacement first, you fix the deformation first, and then you will measure the corresponding stress within the material. So we are going to draw what this stress-strain diagram looks like in different types of materials. And for this, we are going to consider two cases. One where you have a brittle material. So a brittle material is a material that breaks in a catastrophic way when it is subjected to some stress. So example of brittle material would be either glass or concrete. Those are examples of brittle materials. And we're also going to consider the case of ductile materials. An example of ductile material would be, for example, steel. In the case of a ductile material, unlike brittle material that tends to break in a catastrophic way when you reach a given stress, ductile material, they tend to break in a more continuous way. For example, if you take a steel, it's going to be deformed continuously before it eventually breaks. So the difference between ductile and brittle is about the mode of fracture. Very catastrophic for a brittle material like glass, or whether you're going to have more deformation before the eventual fracture for a ductile material. So now let's look at, for both types of materials, what does the stress-strain diagram looks like. So again, the diagram is simply for a given material, you impose a given deformation. So you impose a given strain and you measure the corresponding stress that is applied within the material for this deformation. So we are going to draw the same diagram in the case of both a brittle material and a ductile material. So let's start with the case of the brittle material first, because it's the most simple. So in the case of the brittle material, what you would typically observe is that initially, when there is no strain, then there is no stress. So this is always true. No strains mean no stress. If you don't apply any deformation, then there is no stress. Or if you don't apply any stress, then there is no deformation. Now, when you start to increase the deformation of the material, then you will have more and more stress building up within the material. Or another way is that if you apply more and more stress, then the material will elongate more and more. And in this case, the stress is going to be proportional to the strain that you apply to this material. So you will see a curve that looks like this, where the increase in the stress is proportional to the increase in the strain. So this is going to go up to a certain point, and at a certain point that we can write as the point A, then the material will break. And so the point at which the material is going to break, so we can define at which stress the material breaks or at which strain the material break. So we are going to define the strain at which the material break as the ultimate strain, epsilon ultimate. That is the strain at which the material breaks. The point A is going to be defined as the fracture point. And the last quantity is the stress at which the material breaks. This is what we defined last time in the previous chapter as the ultimate stress. The stress at which the material breaks, this is the ultimate stress. If the stress exceeds the ultimate stress, then the material will break. So this is what you would see for a brittle material. Initially, the stress increases linearly with the strain until the material breaks. And as soon as it breaks, then the stress goes back to zero. There is no stress within the material after it is broken. So in this case, that is simply what the stress-strain diagram looks like for a brittle material. So now let's consider the same stress-strain diagram for a ductile material. So in this case, again, same thing. We take this material, we gradually deform it by increasing the strain of the deformation. We pull the material, we increase its length more and more, we increase the strain, and we measure the corresponding stress within the material. So exactly the same thing. So ductile material will behave very differently from brittle material. So let's see how they behave once you start to deform them. The first thing that they will do initially is that, again, for a strain of zero, the stress is zero. Or for a stress of zero, the strain is zero. No deformation is observed when there is no stress. Then initially, at very low deformation and low stress, ductile material tend to behave similarly as brittle material. The stress will increase linearly with the strain up to a certain point at which ductile material starts to behave differently than brittle material. Then at a certain point, then you have a second regime where now the strain will continue to increase, but the stress will remain constant. So that's a second domain, and we are going to talk more about this domain. That's going to be the second stage of the deformation of ductile material. So that's going to be a stage where the strain continues to increase, so the deformation continues, the material becomes longer and longer, but the stress remains the same. Then you have the next stage where again the stress will start to increase again. So you continue to deform the material more and more, and the stress now starts to increase. So that's going to be the next stage of the deformation. And finally, the last stage of the deformation is that now the stress, despite the fact that the material continues to increase its length, you continue to increase the deformation, the stress will start now to decrease. And at this point, the material is going to break. So those are the different stages of the deformation of a ductile material. So same thing, we are going to define several quantities. So this is going to be still in this case here the fracture point. This is the point at which the material break. So and in this case we are now going to look in more detail at the different regime of the deformation for brittle and ductile material. So in the case of the brittle material, there is only one regime, which is the regime where the stress is increasing linearly with the strain. So this is the same regime that you would find at the very beginning for low stress or low strain for ductile materials. But ductile materials will then show a second, a third, and a fourth domain. So now let's look a little bit in more detail at each of those domains. So the domain 1, this is the domain where the stress is increasing linearly with the strain. So this is what we call the linear elastic domain, the linear elastic region. So this is the first behavior that all materials will initially exhibit. Initially, the stress will increase linearly with the strain, and in this case, the deformation is reversible, which means that if you increase the strain, the stress will increase, and if you decrease the strain, the deformation will just be simply reversible. Everything will go back to the initial shape and the initial length of the material. This is the elastic regime where the deformation is fully reversible. So this is the linear elastic region, and this is the same region that you have in ductile material. Initially, you have this linear elastic region. So that's the stage number 1. So again, in the case of brittle material, this is the only stage that you have. You have a linear elastic material until you reach the fracture point. So now in the case of ductile material, after you have after you exit the linear elastic region, you enter a new stage where now the stress remains constant despite the fact that the strain continues to increase. So this is called the yielding region. This is the region where the material is yielding. So this is the yielding region. So this is where the material is yielding. So in this case, the yield of the material is associated to some atomic transformation within the material. So you have some dislocation forming within the material that allows the material to continue to increase without increasing the stress. So that's going to be the second stage, right? So if we summarize so far, we have the first stage, which is the linear elastic regime. So linear elastic regime, and this first step was reversible. In this case, the stress is proportional to the strain, and in this case the deformation is reversible. Deformation is reversible. That is the case of the linear elastic regime or the linear elastic region. So now we move to stage number 2, which is the yielding. So now in the case of the yielding, the first thing is that the stress remains constant despite the fact that the strain continues to increase. And the second key difference is that now the deformation will become non-reversible, in the sense that if you start to increase the deformation like this, and if you enter the yielding domain up to, for example, a given point here, now if you were to unload the material, the material would remain permanently deformed. Even if you go back to a zero stress, you would see a residual strain epsilon. So in this case, it means that the deformation is not reversible. You apply a given stress to the material becomes deformed, and then you remove this stress and the material remains permanently deformed. If we draw what it would look like, so you would increase the stress like this. At some point you would enter the yielding domain, and after you unload the material, then the material remains permanently deformed. Its strain remains non-zero despite the fact that the stress is zero, which means that the material is permanently deformed. So in this case, now you will have some permanent deformation of the material. So this is a key difference between the elastic regime and the yielding regime. Now you start to have some permanent deformation of the material. So this is going to continue up to a given point, and in this case we are going to define the stress at which you start to see this yielding. We are going to define this as the yield stress. The yield stress is the stress at which you start to see some yielding of the material. So the yield stress is the stress at which the material starts to see some plastic effect, where the deformation becomes non-elastic. The deformation becomes non-reversible. That is the yield point. So now, after this, we enter stage 3. So stage 3, we are going to refer this as the strain hardening region. Strain hardening region. And so we're going to see why this is called the strain hardening. So in this case, in the strain hardening, the stress now starts to increase again as you increase the deformation, and the stress is going to increase up to a maximum point, and this maximum point is the maximum stress that the material can possibly undergo. So this is what we previously called the ultimate stress. That's the maximum stress that the material can possibly undergo. So this is stage 3. This is the strain hardening region. So why is this called strain hardening? So let's focus a little bit more on this strain hardening region, or this strain hardening regime. So strain hardening regime. So let's focus on this strain hardening. Why is this called strain hardening? So in this case, now if I draw the stress strain curve, so we said that initially as I increase the strain, so initially the stress is increasing linearly with the strain, that is the elastic domain. Then you enter the yielding domain. At this point, the stress starts to be constant despite the fact that the strain continues to increase. And now after this, you start to enter the strain hardening region. At this point, the stress starts to increase with the strain. So now the question is, what happens after the unloading of this material? If from this point you unload this material, again the deformation is going to be non-reversible, and typically in this case, when you unload these materials, the stress will decrease with the same slope as the one that it had during the initial elastic domain. So this is what it will look like. So again, if I draw it on this plot here, for example, if you go up to this point and then you unload the material, the stress will decrease while having the same slope as the one it had during the initial loading, during the elastic domain, the linear elastic domain. So this, so far, again, this tells us that once you are in the strain hardening regime, in the same way as when you were in the yielding regime, the deformation again is non-reversible. You have a non-reversible deformation. But in this case, what is the difference between the strain hardening regime and the yielding regime? The difference can be seen when you load the material. So you load the material a first time, then you unload the material. And now the question is, what happens when you reload the material again from this point? So after you load and unload the material a first time, then the material remains permanently deformed in the sense that the strain epsilon becomes non-zero despite the fact that the stress sigma becomes zero. So it means that now the material has a permanent residual deformation. And once you reload the material from this point, this is what it's going to look like. And so if we think about what happens here is that initially when you reload, the material is going to behave exactly like it was a linear elastic deformation. It's going to behave where the stress is increasing linearly with the strain. If I draw it here, it means that after you reload the material, this is how the stress will behave. And after you continue loading, then everything is going to continue from this point. So you will have more strain hardening. So why is this called strain hardening? It's called strain hardening because after you load and then unload the material a first time, the materials becomes harder. Remember what we define as meaning of harder. Harder means more resistant to plastic deformation. So what does it mean here? Like, why is it harder? Why? Because initially, when you first start with your initial material and before any loading has been applied, so initially you have the linear elastic domain, and then at a given stress, which is the yield stress, the material will start to show some plastic deformation, some non-reversible, some non-elastic deformation. So you have a given yield stress. Now the question is, after you have loaded and then unloaded the material remains now permanently deformed. Now when you reload this material, so initially its stress will increase linearly with the strain again. So you will have now a linear elastic domain up to a given point where again the material will start to show some plastic deformation, where if you were to unload it after this, again it would be permanently deformed. So it means that now, after you have loaded and then unloaded the materials becomes more resistant to plastic deformation. It won't show any plastic deformation until it reaches a new yield stress sigma y, which is now higher than the initial sigma y of the materials before the initial loading. So it means that the material is now more resistant to plastic deformation than before, and it will remain, it will continue to behave in an elastic fashion, a linear elastic fashion, up to a higher stress than before. So it's going to be more resistant to plastic deformation. So the materials becomes harder after a first deformation. So this is why this regime is called strain hardening, because due to this deformation, the materials now becomes harder than what it used to be. It's able to reach higher strain without showing any plastic deformation after it has been permanently deformed a first time. So this is why it's called the strain hardening regime. And then the last regime after that is that at this point, the stress, despite the fact that you are continuing to deform the material, the stress is actually decreasing. So this is what is called the necking region. So this is the fourth stage of the deformation, which is the necking regime. And in this case, the material starts to show some necking. So what does it mean to show some necking? It means that if you continues to elongate the material, at some point the material will start to show some necking like this. The material will become thinner at the middle. So you continue to deform the material, it will start to be deformed where it shows the formation of a neck like this. So you have some necking occurring in the middle of the material, where the middle of the materials become thinner and thinner. And in this case, this is a permanent deformation. So if you unload the material will remain permanently deformed like this. The necking will remain even after you remove the stress, or even after you remove when you stop applying any load on the material. So this is another type of non-reversible materials, where now the cross section of the materials, the area of the cross section here, starts to decrease. And this is the necking, and this is why the stress becomes smaller, because the cross section of the materials becomes smaller. So that's the fourth stage of the deformation of a ductile material. So again, for a ductile material, you have those four stages. Initially, at low deformation, it behaves like a brittle material in the linear elastic domain. Then at some point it will start to show some yielding. This is where you start to have some non-reversible plastic deformation. Then you have some strain hardening, which is when the material will now start to exhibit an increase in the stress with the strain, and then eventually you have this necking that is responsible for a decrease in the stress, despite the fact that the strain continued to increase. So in this case, this curve here is a little bit schematic. It's not necessarily at scale, but those are the four stages of the deformation of a ductile materials. So what we are going to see next is, specifically in this class, we are going to focus primarily on this initial linear elastic domain, where the stress is proportional to the strain. And in future classes, you will focus more on those other stages of deformation when you start to have some plastic effects.